know why. All right. Okay. All right. So we're talking about greedy algorithms. And now let's look at the example of the satisfiability problem, where we have a Boolean expression. We're looking at how to assign the different variables in such a way as to make the overall formula evaluate to true. So this is a classical decision problem commonly used in artificial intelligence. Here's an example of two where we have two different clauses and the truth assignments that can satisfy this this expression here. Okay, the question is now, what are some different greedy approaches that we can define for satisfiability? For example, for each variable, let's say if we take the variables in random order, here we had 3 variables in the previous example, we could say that we want to assign a truth value that will result in satisfying the greatest number of currently unsatisfied clauses. If there are multiple such cases, choose randomly. So this is just an example of a greedy heuristic or a step that we could define. This is an example of a dynamic greedy decision heuristic. Why dynamic? Because it will depend on the previously assigned variables, because in each step, we're looking at the number of currently unsatisfied clauses. So if we have already satisfied a certain clause, it's not considered anymore. Let me show you an example. Let's take this as an example, this expression here as an example, and let's say that x1 first. So we take x1 and we look, okay, if we assign it to true, then we have satisfied 2 clauses, the second and the third clause. If it's set to false, it satisfied only 1 clause. In our case, if we simply defined our greedy algorithm as we stated just a moment ago, then our greedy algorithm would assign x1 to true. However, this of course would not be a good idea because the first clause would always be false, and thus we would never evaluate to true. So one step would be to avoid, first of all, if assigning a certain value automatically sets one of the clauses to false, then take the other value. Okay, so this would be one example. Let's say we take the order of the nodes differently. So let's say we consider x2 first. So if x2 is set to true, then 1 clause is satisfied, the second one. If x2 is set to false, then we haven't satisfied any clauses. So we set x2 to true, that's our first iteration. We've satisfied this clause x1 or x2, and we no longer consider it. Now we consider x3. If x3 is set to 1, then 1 clause is satisfied. If it's set to false, 0 clauses are satisfied. We therefore set it to true, and now we've satisfied also this third clause. We no longer consider it. Now we look at x1. If it's set to true, then 0 clauses are satisfied. Keep in mind that now we only have this one remaining clause, right? These second and third we've already satisfied, and we're not looking at them anymore. If x1 is set to false, then only 1 clause is satisfied. So we set it to false. Again, why is this considered a dynamic greedy decision? Because the number of clauses in each step that is going to be satisfied by a certain value, true or false, is going to depend on what we have done previously. So which clauses we have satisfied previously. Okay, I hope that's clear. Again, stop me if you have any questions. So this is just a simple example of a greedy approach for satisfiability. Of course, there are, sorry, go back for a second. There are different different things that you could do, such as look at the variables which show up in the clauses with the smallest number or the largest number of variables. So there's no really, or for example, when you're looking at which order in which to tackle the variables, look at, as I said, the length of the clauses in which they appear. So there's no really greedy algorithm which is applicable to all satisfiability problems, right? So there are different approaches which you can use. Let's look at an example of graph coloring. So graph coloring, we know that given a graph, we want to color its node with the minimum number of colors such that no 2 adjacent nodes share the same color. And I mentioned this example, I think in the first lecture, but just want to go through it now. So an example of a wavelength assignment problem, which can be mapped to a graph coloring problem. So this is an example of a graph, but let's look at this wavelength assignment. So this is a realistic problem in optical networks where And WDM is a wavelength division multiplex network. We're looking at this routing scheme. So we have, this is our actual physical topology with these. So these black lines show our actual physical topology in terms of optical fibers. And these red lines represent so-called light paths or routing schemes. So for example, node 1 wants to communicate with node 6. Node 1 is also communicating with node 4, also with node 2. Node 2 is communicating with node 5, and so on. And these are referred to as light paths or all optical connections. Now, what we want to do is we want to try to assign different wavelengths to these connections. However, we have to take care of two constraints. One is the wavelength clash constraint, which says that light paths that go along the same physical link have to have different wavelengths assigned. So for example, light path demand 4 and 1, they will follow the same physical link over here and over here, in which case they are not allowed to have the same wavelength. Also, the wavelength continuity constraint, which says that we want to use the same, so one light path will use the same wavelength for the whole physical path. And what we can actually create here is something that we call a conflict graph, where the nodes in this graph actually represent these different connections, so these different light paths, LD1, 2, 3, 4, and 5. Okay, so these are our nodes. And the links are connections which cannot use the same wavelength. So for example, if 1 and 5 are using the same physical link, for example, here, then they will be connected here. We see that 1 and 4 are also using the same link, therefore they will also be connected. 1 and light path 1 and light path 2 also, they use this as a joint physical link, therefore we also connect those two nodes. 2 and 4, light path demands, so this is 2, this arrow over here. This is 4. They also overlap along this physical link between nodes 2 and 4. So they are also connected and so on. So we've created now this conflict graph where, as I said, the different light path demands are shown as nodes and the edges represent those connections that cannot use the same wavelength. Okay, and this is, in that sense, we can solve this as a graph coloring problem where now we're trying to find what is the minimum number of colors that we can use to color this graph, and that will also give us then the minimum number of different wavelengths that we need to solve this problem. This is just an example to show you how, let's say, real life example can be formulated or portrayed as a graph coloring problem. Okay, any questions here? So in this case, we can color this with 3 different colors, or in other words, we have to assign 3 different wavelengths in order to satisfy these two constraints. So the wavelength clash constraint and the wavelength continuity constraint. Okay, that was an example. One more example of so we have a greedy approach to graph coloring. We can look at different greedy algorithms, for example, where we consider nodes in a specific order and simply assign to each of the smallest available color not yet used by its neighbors. If necessary, we add. Of course, this will depend highly on the chosen ordering of these nodes. And this is an example of a dynamic, again, a dynamic greedy evaluation. So the fitness of a color will depend on what we've colored so far. So let's look again at an example. This was, I think, the same example or similar to what we had with the minimum spanning tree. Let's say that we're going to consider nodes in this order, 1, 2, 3, 4, 5, 6, 7. We start by coloring them. So when possible, we use a color we've already used. Otherwise, we add a new color. 2, 3, 4, we can use the same color, 5, 6, 7, and so on. We end up with 4 colors. If we were to change the order of considered nodes, let's try a different order, 7, 6, 5, 4, 3, 2, 1. And start by, again, coloring the different nodes. We can end up with colors. So this is, again, just an example of a greedy algorithm that we could define for graph coloring to get some kind of an initial solution. Okay, let's look at an event scheduling problem. So scheduling problems are often hard problems to solve simply because they are so constrained and so on. Usually what we're trying to do is try to schedule certain events that have a starting and a finishing time. In this case, so for this example, we could say that a set of the events that are feasible solutions are a set of events that don't overlap. Our objective will be to maximize the number of events which we can schedule. As an example, let's say we want to schedule lectures in lecture halls, so we can't have 2 lectures in the same hall at once. And let's just illustratively look at some different greedy approaches. So let's say that our greedy criteria is we state that we want to schedule the shortest event first. So we start with the shortest events, and then we start by filling in more events as they appear. What we see here with these gray colors, this is the actual events when they take place, and assuming that this is a timeline. So time is going from left to right. These are the durations of the different events. So we have 1, 2, 3, 4, 5, 6 short events, 3 medium-sized events, and 1 very long event, which takes all day. So if we were to look at this greedy approach, we would try to schedule the shortest event first. So we would schedule this first event, then we would schedule the second event, third, fourth, and we would manage to schedule 6 out of these 10 different events, and that would be our solution. So we're trying to maximize the number of events which are scheduled. Okay, and that would also be the optimal solution in this case. Let's say if this was this was the example of our events, so this was the times when they appear. Clearly, if we schedule the first, the shortest event, that would be this event, but then the optimal solution would be to schedule these 2. So once we've scheduled the shortest event, we've used up the lecture hall during that time, and we can no longer schedule these 2 events. So this is just to illustrate how this approach in this case would not lead to an optimal solution. Okay. What if we try to schedule the earliest events first, motivated by the fact that we're trying to better utilize our lecture hall, so start by using available time as soon as possible. Let's say that these are our possible events. Such a greedy approach would give us this solution. So we simply go, okay, we schedule this first event. As soon as it's done, we look at the next event which we can schedule. That's the third one. Second one is out. Fourth one we have to skip. Fifth and sixth. And that would also be the optimal solution. However, if this was the order of events, then clearly our greedy approach would not be the optimal approach. Okay, what if we want to say that our greedy criteria will be to schedule the event with the least conflicts? And the motivation being that we want to allow more events which can still potentially be scheduled. So by avoiding as many conflicts as we can, perhaps we'll be able to schedule more events. So let's look at this case. So if our greedy approach, so our first, this event here has 2 conflicts. So it conflicts with over here and over here, whereas these 2 each have 1 conflict. So we'll schedule those 2 first, and that would also be our optimal solution. What about here? What will our greedy algorithm assign first here? So we want to allow events which have the least conflicts. Okay, you can try to think about that for a second. So our greedy algorithm would say, okay, first we would schedule this event here. Then, okay, we would start with this one, which has 3 conflicts. This one has 4, right? This one also has 4. This one also has 3. So this would be greedy. However, optimally, this would be the solution. So these are some examples of some different greedy, let's say, criteria that we could define when looking at a scheduling problem. So the important thing when you're defining some kind of a greedy algorithm is to define this greedy step, which then will determine how you will construct the solution, and based on how you will also calculate the profit and add elements to your solution. One more example that I wanted to go through is the case of, so we had a project in this course back in 2014-15 that was related to vehicle routing. We also had a similar problem last year. It wasn't the same problem though. So I just wanted to give you some examples from that year. So that year the project was like I said, involved the vehicle routing problem. This is a simple illustration. We have some kind of a depot. We have a certain number of customers which we have to visit. We have some kind of vehicle which is transferring some kind of supplies, for example, to the different customers. This vehicle, let's say a truck, has a certain capacity. So it fills up. We fill up the truck. It leaves the depot. It can deliver resources to a certain number of customers before it has to come back to the depot, refill, and then continue with additional cycles. And the idea is to find the optimal solution which minimizes the costs. So we have certain costs in terms of the distance traveled and so on. So this is the typical, let's say, vehicle routing problem. In this year, we had so for that project, we had something referred to as the capacitated vehicle routing problem with multiple depots. So there are very, very many variants of the vehicle routing problem. This is one of them. So the multiple potential depots can be used to serve customers. So you are given a set of potential depots. You can choose which subset of them you're going to open or use. You don't have to use them all. That's the first thing. So out of the given potential depots, find those which you're going to use and construct the routes that respect the capacity constraints of each route. So we know how much we can carry along one route. So what is the capacity of one truck? So as to visit each customer exactly once, deliver their requirements, and minimize overall costs. The objective was to find which depots should be opened and construct the routes such that overall costs are minimized. Okay. More concretely, and you can again read this slower offline, but the problem was that we were given a directed graph. So we had a set of nodes V, where a subset of those nodes referred to depots. So only a subset were defined as depots. All of the rest were customers. So we had to, that had a fixed capacity demand. We know the weights of each edge. So going from every customer to every other customer and depot, we have all of those weights, and we know their costs. The capacity of a certain depot is set, so they're not all the same, and we have a certain cost of opening each depot. So that's a one-time cost of opening a certain depot. It has a fixed capacity, and that's how much we can serve from that depot. Each customer has a capacity demand, and we have K identical vehicles. Okay, so each has a fixed capacity. They're all the same. We have K vehicles. They're all the same. They all have the same capacity Q. Each chosen vehicle has a fixed cost of F, and it can execute only one route. So once it executes a certain route, it's done. We have to take a new vehicle. Again, we have a fixed cost, which we start with, and then continue. So each vehicle will visit a subset of customers, return back to the depot where it started the route from. To illustrate this, just to make it a bit more clear, concretely, we had one problem instance that had 105 nodes, and they're shown here in two-dimensional space. Out of these 105 nodes, 5 nodes were labeled as depots. These are these red nodes, and all the rest are customers. The distances are Euclidean distances in this two-dimensional space, so which can easily be calculated. And now the question is, given the information in this problem instance with respect to the capacity, demands, costs, and so on, distances, what is the optimal solution? What we see visualized over here is one potential solution, and I think maybe this was the best solution that was found concretely in this for this problem, where we opened up 3, so we used 3 out of the 5 depots. This blue and pink depot were never used, and these are the constructed routes. So we had to cover all customers. Okay, so that was the project. What I actually wanted to just illustrate here is how we could use greedy algorithms in this context. So a good approach would be maybe to find an initial solution using a greedy algorithm, and then further on apply other heuristics for improving the solution, such as, and these are things that we will get to now in the coming lectures, local search, taboo search, simulated annealing, ant colony, genetic algorithms, and so on. So people used different approaches, but as I said, a good approach was to start with finding an initial solution using a greedy algorithm. Okay, the pseudocode is in Croatian. It's okay. I assume you all know Croatian. So here it was just the simple greedy algorithms said that while we have remaining customers, we open a new depot. While there's still capacity left in the depot, we take a new vehicle, and while that vehicle, until it is empty, it will start by going from one customer to the other by picking the nearest neighbors until it is empty. Once it's empty, then it'll come back. So as long as it has enough packets in the truck or in the vehicle, it will keep delivering, and then after that, it will come back. So at the start or the depots, what we could do, a potential improvement might be, not necessarily, order the depots according to the ratio of opening cost and capacity and start with those. So take first the depot that has the lowest ratio cost to capacity and start with those. So that could be an initial suggestion. Doesn't necessarily have to lead to a better solution. Another example could be to do some partitioning first. So split the problem into two phases. And this was just one example of something, of one approach that a student used. So each node is assigned to the nearest depot with available capacity. So we do some partitioning we have here. And then in the second phase, construct routes. One methodology would be as a first node to pick a farthest customer, and then take each subsequent customer to be the nearest one to the last customer, with the rationale being to first visit the farthest customers as soon as possible, and then from then on trying to minimize the route distance. So this, as I said, these are examples of ways to get some kind of an initial solution, and then after that, a good approach would then be to use some kind of improvement heuristics to try to improve the solution by, for example, modifying the certain routes, moving customers or moving branches, and so on. And we'll get to that later on in the course. Okay. Just a brief conclusion. When we talk about greedy algorithms, generally they're easy to understand, easy to implement, and fast. And there are a good approach to find an initial solution. For most optimization problems, they will yield a suboptimal solution. As I said, again, we're focusing in each step on this myopic view. So you're always looking at locally what would be an optimal solution in terms of this greedy step. You don't have this global view. The quality of the overall, the final solution, will be very dependent on a problem instance. So for a certain problem instance, you may be lucky, and a greedy algorithm may give you a very good solution. In other cases, maybe not. In certain cases, they may depend on the starting point, such as, let's say, with the traveling salesman problem, depending on which node we start from, that will dictate the quality of the solution. So one approach could be to do this as a multi-start algorithm if we're not critical on time. So simply try to run the algorithm multiple times, each time starting at a different node. However, what we did see is that some problems can be solved optimally by using a greedy algorithm, such as minimum spanning tree and so on. So Dijkstra's algorithm, these are examples where then there is absolutely no need to use some kind of a meta heuristics where we can actually solve the problem easily. Okay, any questions in this part? Okay, I'll stop sharing for a moment. Okay. I'll put also an example, just like I did with the branch and bound and this linear programming formulation. I'll put a small example of a scheduling problem, which you can try to solve then offline until next time, and then we'll get back to that. So it's a event scheduling problem where you can try to design or write out some kind of a greedy algorithm that would solve this just in terms of pseudocode, and you can try to do this on your own, and then we'll get back to that next time. So I'll put that up also, and I'll put these example problems into Teams as well, so that they're not just on Fairweb. Okay, let me stop recording for a moment.